Here we go, continuing on with DC circuits. In this video, we're going to look at power in circuits and then how to measure resistances, voltages, and currents in circuits. Here we go. So most household circuits operate at about 120 volts. Okay, so when you plug something into the wall, it operates at 120 volts. So suppose you have three 75-watt bulbs that you're going to use in some household circuit. What type of circuit, a series circuit or a parallel circuit, would give you the greatest brightness? Well, the bulbs that operate with the greatest amount of power are the brightest. So, if we find the power dissipated by the bulbs, we can figure out which circuit would give us the brightest bulbs. Let's look at a series circuit first, okay? We know that one bulb will operate at 75 watts, so we can use that to help us figure out the resistance of the single bulb. Now, power is IV, Ohm's law is V equals IR, so if we solve Ohm's law for the current and plug that into the power equation, we get P equals V squared over R. Rearranging this and solving for resistance tells us that each bulb is going to have a resistance of 192 ohms. Okay, so check that out, try that out yourself. Now this resistance doesn't change, it's pretty much constant no matter how much potential difference that we apply. Now if we had just a single bulb here, then we plug it into this circuit with 120 volts, we would get 75 watts of power out of that bulb. It would dissipate 75 watts of power. But we got three bulbs, and we hook them up in series. Let's see if that changes. What we need to do is find the power dissipated by each bulb in the series circuit by first finding the total resistance and then the total current. This will be the same current for each bulb because these are in series, so we can use that to find the power consumed by a single bulb. Now because our bulbs here are hooked up in series, the total resistance just adds up. So 3 times 192, the resistance of a single bulb, gives us a total resistance of 576 ohms for this entire circuit. Applying Ohm's law then, so we can find the current of the total circuit, we've got the voltage of the whole circuit divided by the resistance of the whole circuit, we get 0.208 amps for this entire circuit. So because they're in series then, the current is the same through each bulb. So we can look for the voltage drop across each bulb, and we'd get 39.94 volts. Remember, in a series circuit, the voltage drops add up to that total voltage of 120 volts. Therefore, the power dissipated in this circuit by each bulb is 8.31 watts. This is the power dissipated by a single bulb when they're connected in series. So in a series circuit with three other bulbs, the 75-watt bulb is really an 8.8 watt bulb. So they're not real bright. Now, let's go ahead and repeat this for when the bulbs are in parallel. Our parallel circuit rules tell us that when these bulbs are connected in parallel, the voltage drop for each bulb is the same. It's going to be 120 volts. The total resistance is less than the resistance of each individual bulb. So applying the resistance rule for resistors in parallel, we find that the total resistance of the circuit would be 64 ohms. Now, even though in a parallel circuit, the current is different through each circuit element, these bulbs all have the same resistance. So each will experience the same current. The current through each bulb then is this 0.625 amps. Therefore, the power dissipated by each bulb will be the full 75 watts that each bulb is rated at. The voltage drop for each bulb, since they're in parallel, is 120 volts, right? So that's going to get the full voltage drop. Therefore, each bulb produces 75 watts and is as bright as it is designed to be. So the bulbs are brightest in the parallel circuit. Houses are wired so that all the lights and the things you plug in are going to be in parallel. And in this way, each item has a voltage drop of 120 volts. So one of the things that we can do with this, right, is think about how the current flows through each circuit. In a series circuit, each bulb gets the total amount of current. If one bulb is removed then from a series circuit, the entire thing goes out. However, because the current is able to split in different directions in a parallel circuit, removing one bulb will not affect the other bulbs. So, here's a question I want you to come to class with an answer for, and then we're going to test it out. I've got this circuit here. I've got bulb A, B, C, and D. Which of these bulbs would be the brightest? Which would be the dimmest? What would happen to the other bulbs if I removed one of the other bulbs? So what would happen to bulbs B, C, and D if I removed bulb A? What would happen to bulb A, B, and D if I removed C? So come to class with answers to those questions, and then we'll test it out and see if your prediction is correct. Now let's take a look at what happens when we add circuit elements into a circuit, and then how do we measure voltage, current, and resistance in a circuit. So let's explore this question. What happens to the current when you add a resistor to either a series circuit or a parallel circuit? Well, in a series circuit, the total resistance is the sum of the resistances. So if you add a third resistor, you end up changing the resistance from 2R to 3R. The current then is equal to V over 3R here. So our resistance goes up, which causes our current to decrease. So in a series circuit, when you add resistance, the current gets smaller. If we're talking about light bulbs, then with one light bulb is fairly bright, you start adding more light bulbs, each bulb gets dimmer as you go, and they're all equally bright. Now let's see what happens when we add resistance to a parallel circuit. Remember, in a parallel circuit, the total resistance is less than the sum of the individual resistors. And in our example, because these are equal resistors in here, we can add them in this way, and we end up with a total resistance with two resistors of R over 2. So when we go to apply Ohm's law to calculate the current with just the two resistors, we end up with this right here, where our current is 2V over R. When we add a third resistor, then our resistance becomes 3 over R, which leads us to see that our current then is 3V over R with our three resistors in parallel. This shows us then that when resistance is added to a parallel circuit, the current gets larger. If our resistors are these light bulbs, then as we add resistance to it, each of those bulbs burn equally bright. As an analogy for this, let's think about traffic through, say, a toll bridge. For this analogy, we start out with a single collection point in our toll bridge. If we add more collection points in series, then we end up bottlenecking up the traffic and increasing the resistance, decreasing the amount of cars that can go through, so our current goes down. If we add our toll points in parallel, we can get more cars through. We actually end up decreasing the resistance and increasing the current. Let's take a look real quick at how we measure voltage, current, and resistance. Measuring current, voltage, and resistance is done with the appropriate meter, specifically the voltmeter for voltage, ammeter for currents, and ohm meter for resistance. These are simple to use and are usually combined together in a thing called a multimeter. So let's start with the voltmeter. The voltmeter has a huge internal resistance. To use it, you place it in parallel with the thing whose voltage you want to know. So in this picture, we see two resistor circuit. To measure the voltage drop across this 24 ohm resistor, we have to place the leads on either side of the resistor while current is running through that circuit. The voltmeter, because it's in parallel with the resistor, has the same potential difference across it as does the resistor. So it has this huge resistance, like millions of ohms worth. So the current that goes through it is really, really small. And the equivalent resistance of the parallel circuit that we formed, which is what we're measuring, is essentially the resistance of the single resistor. To measure current, we put the ammeter in series with the circuit. We know that the current in a series circuit is the same at all points in the circuit, so we can accurately measure the current. the resistance of the ammeter is very, very, very small, so that the voltage drop it causes is so small that it's insignificant. This allows us then to be able to accurately measure the current through the circuit. So voltage drops have to be measured in parallel, currents have to be measured in series. To measure the resistance of a component of a circuit, you have to remove that item of interest from the circuit. Then you can hook in your ohm meter. You place it in parallel with that component, and then the ohm meter makes its own little circuit. It provides a small current, measures the current, and gives you the resistance for that circuit. Well, that'll do it for video number 7. On our next one, our final video for this unit, we're going to look at more complex circuits where we're combining parts of a circuit that are in series and parts that are in parallel into what are called combination circuits. And we're also going to look at how capacitors behave in a circuit. See you in class.